I will lead this presentation, SALEMA project journey, main outcomes, challenges, and possibilities, but I will not do it alone. My colleagues from the project, Tutku Özen, from ASAŞ, extrusion company of Turkey, she will present the development we did in the extrusion field with extrusion alloys. And Andrea Bongiovanni from CRF and Stellantis will present the assessment and the path followed by an OEM, by Stellantis, to validate the SALEMA alloys. Okay, next slide. Okay, it's here. Okay. Okay, perfect. Much better if I can control it. So here you have the summary of the presentation. I'm going to start with a project introduction, and I will show you the final video from the project that it was, well, it's very nice and finally done by ESCI, by Laura Durford over there. Then I will explain a little bit about the scrap sorting system that University of Liège and Comet have developed, mainly, well, University of Liège. And then I will explain a little bit the path we did to develop SALEMA alloys. I will focus on high-pressure recasting, okay? But we did the same for extrusion and stamping, well, to follow the same procedure. And then I will explain about the validation and the production of the different demonstrators with the SALEMA alloys. I will myself explain the shock tower by high-pressure recasting done at Fagor, and the hot stamping validation at Gestamp. And then, Tutku will speak about the alloy development and the industrial validation of the extrusion alloys. And finally, Andrea will give us this insight about the procedure that an OEM as Stellantis follow to validate this kind of alloys. Okay, so I'm going to start with the project introduction and the video. So SALEMA address the dichotomy that European Green Deal poses, where on one hand we need high performance and lightweight materials, which are, well, difficult to get. And then, on the other hand, we need to decrease the dependencies from the external sector. So to reduce the critical raw materials imported into Europe and creating a sustainable economy for the future. On SALEMA, as well, Francesca explained before, we explored two different approaches in order to develop this non-CRM dependent ecosystem. The first one, it's by reducing the amount of critical raw materials, mainly in aluminum, magnesium, and silicon. So we are trying to reduce these two elements in aluminum alloys by other elements that are more commonly available, as can be copper, or just by decreasing the amount of these two elements. And the second approach, it's by harvesting these elements from a scrap. And a scrap that quite often is leaving Europe, as the panelists before explained. So this post-consumer scrap is shredded scrap that most of the time, or sometimes, are exported toward less developed countries to produce low-quality aluminum alloys. We want to use it here in Europe to produce advanced aluminum alloys. Okay, so focusing on this second approach, what we have done is, try to close the loop and to recirculate the end-of-life scrap to produce new high-performance aluminum alloys, new high-performance products. And for that, we have addressed two issues that we will discuss it later, but One is the sorting, so improving the quality of the scrap, so to have better scrap with a narrow composition and homogeneous. And the second one has been to increase the impurity level present in alloys, well, to evaluate what's actually happening if we are increasing some impurities that are limiting the presence of scrap in the aluminum alloys. And on the second approach, what we did was to look at the critical raw materials and try to decrease as maximum as possible the amount present in the new formulations. Okay. Okay. And for that, in SALEMA, we target 4 different processes: high pressure recasting, okay, cold and hot stamping, and extrusion that cover about 95% of the aluminum present in a car. Roughly something like that. It's produced by one of these 3 processes. And we have used 5 different demonstrators to validate the new developed alloys. Shock tower produced by high pressure recasting. Also, frontal frame that it's a mixed component. It has one part produced by high pressure recasting and another part produced by extrusion. Then, by stamping, we produce 2 body-in-white parts, a hood that, well, you have there, and Andrea will show you later, and a portion of a B-pillar, but by hot stamping. And then, by extrusion, a battery box profile that, well, all these demonstrators you can see later on the showroom during lunch break. So this battery box profile and also the portion of the frontal frame to be added to the high pressure recasting. Well, and here in this very nice infographic done by ESCI, you can see the 5 components in a car. So they are all in electric vehicles cars, but most of them, they belong to the body in white, can be found in any kind of car, so also in internal combustion engines. So. And in order to do all this, we have been 16 partners working together during the last 3 years. Okay? We have done for each of these 3 processes the same replication. So we have covered the whole value chain with a material development company. So for instance, in the case of high pressure recasting, it was RAF Metal, with Ruggiero here representing it. Then research institution that was doing the support on the alloy development, and then also the support or the optimization for the processing of the alloys. In the case of high pressure, die casting was University of Padova and Eurecat, these research institutions, and then industrial partners that were producing the demonstrators and validating the performance of the alloys. In the case of high pressure decasting, Endurance and Fagor. Okay, Fagor together with Ford as OEM. And the same for stamping and for extrusion with different partners. Then there were other partners giving so transversal support to the general project, as could be European Aluminium and UNE for standardization and policy guidelines, and then also ESCI for communication and dissemination activities. And well, and also very important, in order to cover the whole cycle, University of Liège and Comet that developed the sorting system to recover the end-of-life scrap and provide good and valuable scrap to the project.
In 2023, 288 million registered cars and trucks were counted on the streets of Europe. 10% of an average passenger car consists of aluminium. When it comes to electric vehicles, up to 30% is made of aluminium parts. and the amount of aluminium needed is expected to increase. Aluminium is around 60% lighter than steel. Using it in cars makes them more energy efficient. However, there is a speed bump on the road to more sustainable transport. Aluminium and its ore are considered as strategically important critical raw material, CRM for short. To make it into usable alloys, other CRM is needed, such as magnesium and silicon. In Europe today, we rely on imports from other world regions.
We know that the situation currently in Europe is quite complex, and one of the main concerns is about the raw materials. We are suggesting new alloys with the reduced content of critical raw materials, with maximized content of recycling.
Hundreds of tons of old cars are shredded each day in European scrapyards, a valuable source of aluminium that the car industry had not been able to use until the SALEMA project.
Con SALEMA vamos a desarrollar.
In SALEMA, we develop alloys for stamping, for extrusion, and for the manufacture of structural components by means of die casting, which until now had to be made with primary aluminium. It was only manufactured from pure aluminium. So this will allow us to enter into applications that were not possible until now.
No era posible.
The idea of SALEMA was simple. Change the aluminium value chain from a one-directional to a circular economy. Instead of producing alloys using primary aluminium or imported CRM, which end up in vehicle waste, the waste itself should be recycled as a source for high-end aluminium alloys. The journey of recycled SALEMA alloys begins in Belgium. Here, Group Comet processes 200 tons of material per hour and sorts out the aluminium pieces.
We extract the heaviest fraction of metals, so copper, zinc, brass, lead, stainless steel will be removed from the metal mixture. At this stage, we have a global aluminum fraction that will be further separated into two kinds of aluminium.
Some of this pre-shredded material contains different kinds of metals such as silicon, magnesium or copper. On the other side, there is aluminium with less alloying elements. Being able to accurately sort these different qualities of aluminium scrap is the key to being able to recycle it for even high-performance uses such as car part B-pillars or shock towers. This challenge has been mastered with a new technology called LIBS, laser-induced breakdown spectroscopy, a way of sniffing the chemical composition of the aluminium scraps.
We generate very high-frequency laser beams to hit one metal particles to create a plasma. What is a plasma? It's a fumes containing all the elements contained into the initial metal scraps.
The composition of the plasma is analyzed using a spectrometer and sent through an algorithm which feeds a line of robots with detailed information so they can proceed with sorting. The algorithm used in LIBS is a key innovation developed in SALEMA by the University of Liège.
We have a long-lasting partnership with University of Liège because they've developed huge skills about the industrial implementation of new sensors to be able to process and use huge amount of data in very short period of time. That is the key to make such a technology profitable for industrial partners like Comet.
The sorted aluminium scraps contain a mixture of other materials which affect the properties of alloys. So the challenge now was how to recycle the recovered scraps into high-quality products.
The aluminum coming from recycling is more difficult to be controlled. So one of the efforts of the project is to understand which is the best possible way of recycling aluminum, keeping or improving even the final properties of the alloys.
Inventing a new recipe for high-performing recycled aluminium alloys was therefore the task of the research team.
We started from an hypothesis of 200 compositions. From this composition, we selected the best one from the point of view of the simulation and the prediction of the behavior. We take specimen, we tested, and then we performed the final selection of a couple of alloys for the demonstrators.
Demonstrating that the new alloys would meet the needs of industrial players in the value chain was a crucial goal. Here, Italian company Endurance got busy. As an industrial foundry that casts metal parts for cars, its role was to test how the recycled alloys would work in practice.
In our business, we have to produce sound casting at the end of each single shot. One critical point that we have to consider is the design of the gating, which is the flow of the metal before entering the part. That has to be carved into the steel of the mold and is very crucial to the success of the filling and solidification of the casting.
Changing the chemistry of an alloy changes the way the molten aluminium enters and flows through the mold. This is critical for the quality of the car parts produced in the casting process.
Knowing the thermophysical properties and fluidity of this alloy knowledge will help to design the next casting with a more robust base of information, meaning that we should be in condition to design the mold and the process to be successful from a scrap point of view, reducing the risk of having quality issue on the parts. So all the effort done so far will help us to reduce the time to market of the SALEMA alloys when those will be required by our customer.
The newly made parts and the alloys were tested over and over again by both the industrial and academic partners to ensure they meet the high-performance needs of the market.
In the project, we are testing, first of all, the microstructural features of the alloys, so the way in which the elements are generating the structure of the material, and then we are performing the mechanical testing. We have a lot of requirements from a mechanical point of view by the end users, and we are checking in the specimen if they are satisfying this requirement. This casting is very nice because it will be useful also for showing to our students the potential of aluminum associated to the foundry process.
Future generations of metallurgists and engineers at the University of Padua will learn the project's alloy design methodology, which will also work for other kinds of metals. And there are other benefits too.
A largo plazo, los desarrollos...
In the long term, the developments achieved in SALEMA can be applied to many different sectors. All those where requirement aluminium alloys are used, such as automotive, railway, aeronautical, naval sectors.
Automotrices, ferroviario, aeronáutico, naval, hasta...
To sectors that have nothing to do with movement, such as at the structural level of aluminium carpentry, other structural applications and many other sectors.
Otras aplicaciones estructurales y, bueno, muchos otros sectores.
SALEMA's aluminium alloys are ready for mass industry uptake, contributing to Europe's goals for more sustainable transport and reduced reliance on imported primary and critical raw materials.
Okay, so, well, after this introduction and this very nice video, I will move on with the scrap sorting system. So, it's a very important point of the project. The objective and the work was mainly carried out by University of Liège was to adapt a picket sorting prototype to separate post-consumer scraps based on their alloying elements with the LIBS, with the laser-induced breakdown spectroscopy. And they succeed in producing high-quality scraps for, lots of 1,000, 2,000, 3,000, the different series, and also a fraction reaching in casting alloys that was used for the different aluminum alloy producers, the SALEMA's partners, to produce the alloys for the project. Without going into much detail, the methodology this scrap sorting system uses is they fuse different technologies a 3D camera that recognizes the position and the geometry of the object, of the piece of a scrap. Also, a camera that recognizes the color, and then X-ray measurement to measure the more or less the chemical composition, and finally the LIBS, the laser-induced breakdown spectroscopy to have the actual chemical composition. And all this information is processed by artificial intelligence and their algorithms in order to give the information to the robotic arms that are picking the scrap piece in the correct position and bringing it to the corresponding box. Okay. Okay. So for that, there are two algorithms, or two processes. First, a multi-output regression model that from the spectrometer given by the LIBS, they predict the chemical composition of the material, of the piece of scrap. And then once we have this chemical prediction, there is a second model that decides to which box, to which classification it belongs, this piece of scrap. And here you can see the prototype working on real time. And you can see that it's quite effective and quite fast. Okay. Once presented the scrap sorting system, I will go into giving a overview, very high-level overview of the development procedure used for SALEMA alloys, focusing on high-pressure recasting. More information about this development, because it belongs to the first work packages, work package 1 and 2. Most of the deliverables are public, and they can find in the project website. So if somebody is interested, he can go to the project website and find more detailed information about the process we follow there. Okay. I think it's not working very well. I'm pushing the button and it's okay. So for instance, for high pressure recasting, on the development of alloys with high recycled component, we work on 2 levels of magnesium, medium, moderate level, about 0.3, and a low level, in order to get better ductility. And then we change the amount of impurities, focusing on the ones that, together with the industrial partner, with the aluminum producer, we found as the most restrictive in terms of being able to get this alloy from a scrap. That they are mainly iron and copper. Also, zinc could be a limitation, so we tried what happened if we increase it. And we change slightly the amount of manganese, going to 0.5 to 0.6 in some alloy variants. Okay. To assess the performance of this alloy, first, before going into high pressure recasting process, we did it this general screening with these 15 alloy variants, where we measure flowability of the alloy, okay, with a mold and a technique defined at SALEMA, and that is currently under standardization. We are right now publishing a pre-standard, sense analysis pre-standard, CWA, that it's going to be published within a few weeks. And and with that, we were able to check a small well, how small variations on chemical composition could affect alloy flowability and then the ability to fill the part and to get a good part with high pressure decasting process. Okay. Here, for instance, we can see that zinc, a small increment in zinc, decreased quite a lot the alloy flowability. And also we check the mechanical properties on the plates produced by gravity casting, but well, are not representative of high pressure decasting. From that, we select the most interesting alloy variants. Actually, we test 8 different alloy variants that this, yes, we use our high pressure decasting machine in Eurecat to produce a plate, a 3 millimeters plate, where we measure the mechanical properties in the cast condition. And we found that already in the cast condition, most of the alloy variants met the requirements in terms of yield strength and ultimate tensile strength of one of the demonstrators, the shock tower. With the other demonstrator, we had more trouble, but maybe with a heat treatment, after the heat treatment, we could reach those requirements. And the biggest issue we had it with elongation that, well, without heat treatment was not reaching the minimum requirement. And then, one slide back, sorry. Then for alloy development, so we made, additionally to this scrap alloy, high scrap content alloys, we work on new alloying systems with lower silicon and magnesium content. For that, we define what we previously defined in another project, CRM content, a criticality index, we call it, that gives us a value of how critical the alloy is, and it depends on the elements that the alloy has. And then we predict by using, well, at the University of Padua, they predict by using thermocalc, thermodynamical simulation software, and in some cases, their own elaboration, as can be seen here, for example, for hot tearing, where they determine the gap, well, the temperature gap for the terminal freezing range, that is the solidification from 95 to 100%. So, and with that, we had a proposal of over 150 alloy variants, different compositions. We evaluate the critical index, and also with this, with the model, the castability of the alloy by measuring the predicted viscosity by thermocalc and the other factors. And then we weighted 1/3 for the criticality index and 2/3 for the processability, as well. It's more important be able to produce the component than the criticality of the alloy. And with the weighting, we rank the alloys, well, from the best scoring to the least. And from this scoring, it was selected the 7 better alloy variants. Well, one back, sorry. So we select 3 alloy variants for aluminium magnesium 2 family. That was one quite good scoring family, and 4 variants for aluminium silicon 8 manganese magnesium alloys. Parts were produced by high pressure recasting, and then the mechanical properties were determined for those parts. And again, without heat treatment, the yield strength and the UTS requirements for the shock tower could be met. For the frontal frame, we expect that, well, we expected in this time that with a heat treatment, we could reach it. And yeah, and here also elongation, well, more or less meet in some cases, because the minimum requirement is 10%. In some cases, it was in the limit. Okay, and from that, we will move on the next point, the validation of the high pressure decastings with one of the demonstrators that you can see later on the showroom, the shock tower. For that, what we had, I don't know if I'm not pressing properly or what, that's trouble. Okay, what we had, it's a shock tower that it's a component defined for the project, but defined by Ford, the OEM, and that we produce it with aluminum, silicon, tin, manganese, magnesium as standard alloy, so 43500 alloy. And here you have the mechanical properties in the cast condition, and after a T7 heat treatment of 1 hour at 480 degrees C, and then artificial aging of 2 hours at 230. Okay, and well, the mechanical requirements of the shock tower were met. That it's 120 megapascal for yield strength, 180 for ultimate tensile strength, and 10% of elongation. From here, should I point somewhere or it's okay? From here, in order to move to the new alloys, the first thing we did was to characterize the properties, the thermal and physical properties of the alloys required by simulation software in order to simulate the filling and the solidification of these new alloys with the shock tower geometry. So we did it for the 3 alloy variants we were going to test with this alloy, and we measured the required properties, latent heat, liquidus and solidus temperature, and also the specific heat at different temperatures. Okay, and with this input, we went to simulation. Here you have the basic of the simulation we carried out, the geometry, the mesh, and the conditions. Okay. Oh, sorry, come back. And then we had the results of the simulation. So we observed that with the partially recycled aluminum, silicon, tin, manganese, magnesium alloy shouldn't be a problem to cast the component. The simulation was, even if we had a small, higher iron content, copper and zinc, the flowing conditions were mostly unaffected. So, and the filling was very similar to the base alloy. For the aluminum, silicon, 8 manganese, magnesium, and especially the aluminum, magnesium 2, it was different. We observed that there was higher cooling, and it could be a freezing region just here. I don't know. Oh, okay. Okay, there is no pointer. Well, so you saw on the top this blue, dark blue, that it's colder, that it can represent a problem. So we needed to increase melt temperature and or the injection speed in order to get a good quality component. And for aluminum magnesium 2, also we observed the same thing, but well, the main issue actually that we had in the, okay. The main issue we had finally in the validation, in the production of the parts, were related with cracking and hot tearing. So here you have the results for the benchmarking, so the base alloy, the standard aluminum, silicon, tin, manganese, magnesium alloy, 43500. The properties I showed earlier, And then for the variant 6, that it has a higher amount of iron, about 0.3, but also a higher amount of copper, 0.1 maximum, and higher amount of zinc, 0.1 the max. And we reach similar mechanical properties in both as cast and after the T7 heat treatment, just, well, little bit lower elongation, but it's almost not noticeable. Then for variant 7, instead of a T7 heat treatment, it was tested partial, well, an annealing treatment, and with that, 2 different temperatures were tested at Fagor, okay, 320 and 380. With the 320, 1 hour, we observed that mechanical properties remain almost unaffected. So actually, we are losing ductility and a little bit of yield strength. So, and with the 380, we reach the minimum required elongation. So we were successful in getting more ductility, but unfortunately, with the cost of losing some hardness, some yield strength that went below the minimum requirement. And then for the aluminum magnesium 2, the main issue was that with this complex part, it was difficult to have it solidified within the die without cracking. So the mechanical properties were almost reached without heat treatment, but with high dispersion in terms of ductility, depending of the region where you were testing. And so, and also for, well, in the project, I have taken this slide as example, but it's an important thing, and we have looked careful within the whole project to make the, well, also to take care of the life cycle assessment and the environmental impact of these new alloys. And for instance here, we evaluate the global warming potential of the new alloys compared with the baseline. And we observe that with some alloy variants, as can be the variant 6, which has been pretty successful, we can even almost decrease 75% this global warming potential. Okay. Okay. That regarding high pressure decasting. Then I will shortly present also the alloy development process followed for stamping. On stamping, we select 2 alloys for the partially recycled development. One, the 6181A, 6,000 families alloy, and 5754, 5,000 series. And we did it with 3 different recycled contents for the 6181 and 2 different recycled contents for the 5754. Okay. Due to this increment in recycled, it was necessary to increase also the level of impurities, mainly iron, copper, manganese, magnesium, but also we increased a little bit silicon on the 6181 and zinc in order to allow this higher amount of recycled content. In this 5754, only iron was increased in the 80% recycled material. Okay, sorry, I went. So the first thing we did was to measure the tensile properties of those alloys, and we observed that, so with the static properties, the values remain unaffected, independently of the scrap rate used to produce the alloys. Elongation was very high, even with 85% of scrap, in both alloys, 6181 and 5754. But once we look at the formability of those alloys, well, we had small surprise. So for 57, 54, where only iron need to be a slightly increased, almost no difference was observed in formability, and the formability parameters remain the same. But for 61, 81, we observe a pretty big change in the formability parameters and of reduction by increasing the amount of scrap. So, and this observation could be, well, was also done by measuring another property that gives better insight than just the tensile test, that is the essential work of fracture, a toughness measurement developed by Eurecat, and where we have also a standard going on, that it's developed in order to measure toughness in sheets, so in very thin specimens. And here for 5754 alloy, no difference was observed, so we had a cloud of points that could perfectly belong to the same kind of material, okay, two straight lines that almost fit. But for 6181A, we observed that the values were pretty different. So also a loss in toughness was observed in this kind of material when we increase the amount of recycled content. But nevertheless, okay. Yeah. So we want also to measure the formability, FLC curve, and we've observed that in the 5754, almost both curves fit, not lost in formability, but in the 6181, there was a change in the alloy formability. But if we put all these curves together, we see that even in the 6181, we are losing formability. The new formability, it's more or less in the level of the 50,000 alloys. So, and it's not that big loss, so it's quite good still, the formability. And well, so we were pretty happy and sure that these alloys could also be used to form complex shape components by stamping. And okay, I went. And so then for the final validation of hot stamping, we select this 6181 alloy with a high recycled content, 85%, and also a 6111 alloy that was from the point of view of trying to reduce the critical raw materials content, as it has lower silicon and magnesium than other typical 6000 series alloy. And we tried to implement it into Gestamp production plant. Okay. In order to have this implementation, several things have to be done. First, well, here you have the procedure that it's followed by Gestamp when they are developing a new component. First, going to the part design, then the simulation. Then with the process information, they set the process conditions, produce the tooling, and then the final thing we did was to produce the tryouts with the new SALEMA alloys. Okay. So regarding process simulation, so we characterize the properties of these new alloys at different temperatures and strain rates. And also by Gestamp, they did this friction test characterization that they bring in order to fit their model, the simulation software. And here, well, in the first simulation, so the one in the left of the two simulations, you can see that there are some marks, some critical zones that with a small change in geometry, but having a higher draws there, it could be avoided this problem. So this simulation was useful in order to define this final geometry with these draws in order to have better, better final quality of the produced components. Then, in order to define the process parameters, we did at our lab at Eurecat with dialectometer replicate the heating conditions for the stamping process, taking into account what Gestamp can reach in their plant, and also different post-heat treatments, agent heat treatments, in order to get the prediction. And then in Gestamp line, the sheets were heated and pressed in order to replicate the actual working conditions, so the process. And from that, tensile tests were conducted to validate the final properties that if we're reaching or not the requirements. Okay. And with that, so we define the processing conditions in parallel with this input and the simulations. Gestamp built the tool. And finally, sorry, okay. I have trouble with this. I hope it's only me and not the rest of the speakers. Oh, okay. Please, one back. Okay, here. And finally, I'm really sorry for, but well, I'm finishing, so I hope that the next speaker is better than me with this. So finally, we had the part production at Gestamp pilot plant, where they produce the different, the parts with the two alloy variants, with the different tested alloy variants. And we are currently measuring the mechanical properties and finishing the characterization of these parts. And well, that was all from my side. So right now, Tutku will present you about the alloy development and industrial validation in extrusion. And
thank you, Manel. I have this one. Yeah. Thank you, Manel, for the great information that you have shared about our project, SALEMA. And I'm Tutku Özen. I'm working in ASAŞ Aluminium in Turkey. I'm a metallurgical and materials scientist, and I continue my PhD degree education in Istanbul Technical University. Now, today, I'm going to give you a brief information what we have carried out in the SALEMA project with respect to extrusion industry, aluminum extrusion industry. In order to begin with, this is a scheme of aluminum extrusion methodology. First, the main step is making the alloying. In automotive industry, for extrusion alloys, we are generally using 6000 series aluminum alloys. And the main alloying elements of 6000 aluminum alloys are magnesium and silicon, which are the critical raw materials, one of the critical raw materials. Within the scope of this project, the uniqueness of SALEMA comes from we are trying to use not magnesium and silicon as a tablet, but substituting them from scrap, post-consumer scraps, well-sorted ones, actually. After alloying steps, we carry out with the direct chill casting, and we have done the homogenization in order to make beta phases distribute all over the microstructure. After that, extrusion BS has been cut into the length, and they have preheated to be able to extrude them. In order to explain a little bit about extrusion, who is not familiar with this process, you can imagine like squeezing a toothpaste from its container. You will be having a tip shape of the container tip shape of the toothpaste on your toothbrush. So extrusion is something like that. We are preheating the extrusion bed and squeezing it from the extrusion die, which gives the exact shape of the extrusion die to the aluminum profile. After that, these aluminum profiles are heat treated upon 2/3 of its melting degrees, changing with the alloy especially, and in order to sustain the mechanical properties by solid solution hardening methodology. As you can see in this project, we have worked with 3 different alloys, and for each alloy we have worked with 3 different variants in the beginning. 6111 alloy was coming from the suggestions from the University of Padova, and 6063 and 6082 was coming from the industrial experiences where we commonly use this kind of materials in the automotive industry a lot. After that, it has been validated with 3 different variants. It makes 9, and it's just the beginning at the moment for the trials. In our partner institute, Non-Ferrous Metals Institute in Poland, they have used different scraps coming from the Comet, including electric vehicles components, photovoltaic panels components, scooters or bike components, some things like that. 6000 series and 5000 series mostly, and they have lab scale casted them into the final BS, as you can see in this slide. After that, they have characterized them to investigate their microstructure, their mechanical properties, and also other impurity effects and etc. After that, they have carried out the homogenization studies in 2 different homogenization conditions, and they have optimized the extrusion with 2 different temperatures, 2 different ramp speed. I couldn't multiply because I'm a calculator kid, but you can imagine how much trials have been carried out in the SALEMA project extrusion site carried out. And the different extrusion dies already been used. One of them was flat and one of them was rectangular. They have been investigated via transmission electron microscopy, EBSD, corrosion test. Some mechanical properties are also tested in different conditions. For example, back pain test is conducted to be able to get an idea over how temperature affects its mechanical properties. Bending test, fatigue, and crash performance tests are applied. Upon this, low CRM content alloy 6111 has been chosen with respect to its mechanical properties, especially from bending results, and variant 2 has been chosen. After that, 6063 alloy has been tested mechanically, and with the results of the mechanical properties and the bending test, the variant 3 has been suggested to be upscaled by ASAŞ. And finally, 6082 alloy has been developed, and 3 different variants has been tested, and variant 3 has been suggested to be upscaled, again, with respect to its mechanical properties. Also, as I have mentioned, 2 different dies has been used in this lab scale trials. One of them was flat, and the other one in the shape of rectangle. Hollow profile making is a little bit hard in the extrusion side, and this one also gives us an idea to be able to industrially upscale the lab scale results. For the industrial site, we have begun with casting of the well-sorted scraps from University of Liège partners from Picket system, and we have casted in our prototype casting facility with the capacity of approximately 1 ton. As you can see in the second picture, this is the SALEMA biet that we have casted. It's 14 inches and 1.5 meters long. They have been analyzed ultrasonically in order to see if there is any defects on the biet. It's a non-destructive testing methodology. if there's a void, if there's an impurities or something like that, we have tested, and results are acceptable with respect to ASTM standards. In order to carry out with the extrusion, we have designed a 3D CAD model of the extrusion die first. After that, we have analyzed it with Q-form simulation carried out by ASAŞ, and we have revised a couple of times the extrusion die with respect to the results of the Q-form simulation. The extrusion die geometries shared with Eurecat, our partner Eurecat, and they have make the simulations with Altair-inspired extrude software. They have come up with the related extrusion parameters like its temperature, ramp speed, and also we have get these values from the lab scale trials too. And we have produced the die to be able to carry out with the continue with the extrusion process. In the extrusion practices, we have used the 62 meganewton capacity extrusion press, which is one of the biggest extrusion presses in Europe and the biggest one in Turkey. As you can see in this picture, and also you will be able to see it in the demonstration area too, in the back. This is the SALEMA profile, and also we have also extruded a battery box profile, which is an intersection point of Marble project, which is another EU project. I strongly suggest you to look for it too, and SALEMA project, and it has been also validated with the SALEMA alloy. After that, all of these profiles has been measured in the CMM measurement in order to be sure whether this SALEMA profile, which will be at the end, will be welded to the high pressure die cast part to be able to create frontal frame, are tolerances and geometrically okay or not. As you can see, there are too much characterization and test studies have been planned in the beginning of the project. To be mentioned about them very briefly, first we have go with the imaging of them in order to see the microstructure of the whole materials in the industrial casted and extruded ones. After that, we have carried out some mechanical testing in different conditions. For example, we have carried out anisotropy testing, whether extrusion direction affects the mechanical properties or not. Also, we have carried out bake paint testing, whether temperature affects the mechanical properties or not, or how. And also, we have carried out some bending tests, and these are the tests we have conducted so far. From these, we are able to use these SALEMA alloys in the market, and their time to market has been decreased thanks to the developments in the SALEMA project. Now, my colleague Andrea Bongiovanni can... Yeah, thank you.
Thank you. Okay, hello everyone. I'm Andrea Bongiovanni. I'm studying material engineering too from University of Turin, and now I'm doing a PhD in CRF, that is the one research center in Turin for FCA, now also for Stellantis. I will talk about a contribution of Stellantis and of CRF, so from the OEM point of view and from the laboratory point of view in the SALEMA. And so, how we validated the alloys and how we validated also the component that I will show later. So first, we collaborated on the development of the alloy and the requirement of the demonstrator, and we participated actively on the work packages that were about pressure casting, cold stamping especially, and extrusion, and also the validation. So for the alloy development, with the help of the other partners in the first work packages, we indicated what were the main requirements of the alloys and the components based on real structural components as this one, but also, as I show you later, in the frontal frame. and against the standard alloys and with the internal and international standards that we use for the test and also for the development of the alloys. Just a couple of activities that were done in all the 3 work packages are the corrosion tests, that we have a corrosion department that is focused on that. We did mainly 2 tests. In automotive, the corrosion resistance is provided mainly by the Blackie coat or cataphoresis. So it's a process that create a coating on the component. Usually it's done 2 times on component level, and then on all the body in white it is dipped in a cataphoresis bath. And so with this test we check the compatibility of the alloy, since the main one of the first issues with the recycle is will it behave correctly in the corrosion. And so, for example, you can see on the right a component that that one I think is part of a plate for high pressure die casting that did the cataphoresis. Then manually we did a scratch. Then we did a cast test, so a corrosion chamber for, if I remember well, 168 hours. And then manually a scratch with like a duct tape. And then you evaluate how much of the corrosion went below the cataphoresis. And for all the 3 work packages, so for all the 3 kind of alloys, they were all okay. Then we did something more like laboratory scale, so the weight loss differential to see how much these alloys are corroded. And this is just an example of the casting part. Since I didn't specify, maybe I'm doing the PhD on high pressure die casting, so I more specialize on that. And we can see, for example, how there are some slight differences between, for example, these 2 variants, variant 4 and variant 6, and also some difference between the corrosion after the heat treatment. Obviously, these components will never be without cataphoresis in a car, but it's interesting to see how it behaves. Then the bending that also to explain. In fact, this one is the one on the left is the results of the bending that help us to choose the best variants and the best alloy. And we did also on the casting, even if usually the OEM doesn't require, almost few OEMs require bending test on casting. And again, we had a good behavior, even at sample level. Now we are continuing the characterization on the demonstrator. Talking about the cold stamping demonstrator, so this one, that is, before we were like just playing with it to see, and if you want, you can see how light it is, because maybe sometimes when you talk about this part, so you don't realize how light aluminium is. And this is the inner hood of the Jeep Renegade, and so I don't know if you know the inner hood, then there is plastic for thermal issues and etc. And then the outer part, these aesthetic components. And we produce it with these 2 alloys, one 5,000 and one 6,000 alloy with 2 recycled content. And the mechanical properties are assessed not on the component level, but on the specimen level, but they were very good results. And we produce it with the current stamping plant that we have in Mirafiori, so on the same components that produce the normal production of the Jeep Renegade. We did a bending test, but also cold informing test, because it's very important due to the processability of the alloy. Again, the corrosion resistance, as we've seen before. And then the manufacturing of these components that was done in the Mirafiori press shop with the current machine, as I said before, that does the current components with that you find in a Jeep Renegade. And how it behaved. The 5000 alloy that I think is this one. Instead outside there is the 6000 alloy. The 5000 alloy was almost perfect. We were not surprised, but very happy about that because it could be used for the current production because there were no, from the manufacturing point of view, there were no defects. In the one highlighted are the most sensitive parts because they are holes and so they are like they can break up a bit. So the whole expansion can be a problem. That was a bit of a problem in the 6000 alloy because in these parts also in that one the material can break due to the, as Manel explained before, due to the high recycling in the 6000 alloy, it decreases the formability, and so the ductility and the ability to deform without breaking. And so it is not okay for the current production, but especially the colleagues from the manufacturing department, before doing the test, they say, okay, it's never going to work at 6000 alloy. So small defects like this was a very great achievement from this point of view. And so some design tuning also of the alloy or the die will even improve these aspects. Then for the frontal frame, so for the other light pressure die casting components, we took it from a real frontal frame from the MC20 that is produced with another geometry. You can see on the bottom left the geometry of the actual component. And it is done in another process, low pressure die casting, that for those maybe not more focused on that, there is a big change between low pressure and high pressure, because low pressure you can make like let's say a boxed part. Instead, in the high pressure, you create with nerves and space like in the one on the right. And also, the main advantage to go to high pressure is that you can increase the volume production, because it's a process that can scale up the volume. And also, so decrease the cost of the components for not a luxury car as the one that you see right now, so for also segment C or D vehicle. We use the mechanical requirements that are mainly the same of the low pressure die casting. And this is a video that shows the production of this component that was done in Endurance with the colleague Claudio Mus. And so this was again done by Endurance, so a radiographic check, and it's very good and very sound. Even if the trial that was done was obviously the one of the European project and in an industrial scale, but again, the alloy behaved very nicely, and there are some defects only in the last part. But the important part is the one on the left that we have called it the nose. That is the one that will be then joined with the extruded profile. So that one is very sound and is free of defects. On the demonstrator, then we are doing all the characterization that was done at specimen level with Eurecat and the University of Padova. All the mechanical testing, the one in bold are the one that will be directly done in CRF laboratories. So obviously a study of the microstructure, bending test to see how much can be the difference with the values that were obtained at sample level that you can see with the three heat treatment states, so SCAS, T5 and T6. And then the welding test with extruded alloys. This is done an example of the work that is being done in University of Padova by another PhD researcher, Osama Ashgar, with Professor Bonollo. And you can see how in detail they are going and the good results that were obtained. Then again, as said, the final assembly will be a pressure casting with extruded profile. And we are performing the welding in that area, and obviously the validation that is performed usually in production, so amigography inspection, tensile test, and non-destructive testing, obviously. As a final considerations, from all kind of point of view for the frontal frame mainly, but suitable also for the other process. The alloy is suitable for structural components already with this design. And from the processability, from the manufacturing point of view, there are no major differences or changes to do for producing these alloys with respect to the primary one. And this is a big achievement. Obviously, for the OEM point of view, to increase the TRL for the industrialization, for the commercialization, we need to tune in the design for increase the crash behavior, and also perform obviously some crash tests before putting that in a car. But we see and we participate in other projects that also are European funded and are with, for example, Eurecat or Gestamp or Endurance or other partner of the SALEMA project to improve, for example, the strength and the crash behavior. I've seen recently the simulation of the Frex crash that was done by Gestamp to improve the real crash simulation in a real with the common instruments. And for example, the restore, so to improve the remanufacturing of the components for other vehicles, so or also in other segments. So independently from the quality or cost of the car, but to improve these components. And that's all from my side. Thank you.
Yeah, thank you. So I check and we are well on time. I was a little worried about having 3 speakers if we're going to have time for questions, but I think we have time for a few questions. So if there is any question in the audience for any of the 3 speakers, we will be happy to answer or try to answer it. Yeah, just got there.
Thank you very much. My name is Herman Terrein from Vrije Universiteit Brussels. I think congratulations, it's impressive what you realized and also the way you presented it. I have one question which was already related with the previous question of Ilya of Chemetal, because I'm a surface treatment person. When you started from the scrap, did they contain coatings, or was that all bare metals, or was that an issue, or it was ignored?
Well, so on the post-consumer scrap, there are some with paint, other kind of coatings. We had that into account for both things, for the scrap sorting. Well, fortunately, yesterday and the day before, we had the meeting here, and we were able to visit the University of Liège facilities, and they explained us very well how they deal with it, but they can hit with the lips more than once if there is a coating in order to
ignore the
to remove and
coating,
go deeper and measure the actual aluminum below the coating.
Okay.
And then also, well, here maybe Ruggiero can give us more insight, but we make, they develop a procedure to melt this scrap in such a way that we can have as maximum yield as possible with specific furnaces to remove this coating before actually melting the aluminum. And I don't know if Ruggiero, you want to...
Just two things. Yes, it depends of the quantity or the kind of the coating.
Right.
The plastic, rubber, also the coating. There is a different way to remove this coating. Is that the coater or pyrolysis system is very high. Or usually now we use a specific multi-chamber furnace that are able to preheat and destroy the organic material before the scrap enter in the melting phase. So right now we are able to remove all the part of the coating. We also use this coating like energy instead of the natural gas inside the furnace.
Because excuse me, that I'm just taking one more minute. Because the discussion is, do you need to adapt, let's say, the surface treatment, because there are interface layers and so on, which are also introduced new in the car manufacturing technology at the moment. And if they are introducing problems for the recycled system, it needs to be considered.
Yes, right now we don't find any problem with this coating. We are using specific, this furnace are able to control the level of the organic material to destroy, adapt in base of the kind, the level of organic material automatically.
Can I get?
Not organic.
Oh, okay.
Not organic is usually phosphating.
Zircony or
zirconium is less, it's still phosphating, gives off aluminium, or can be oxalan is silent based, but zirconium based also. Yeah, means this you cannot burn.
But we don't find a very small quantity.
It's smaller than coating.
We are able to use also.
At the moment, the scrap coming from automotive industry are the minor part of the entire amount of scrap we can use.
Yeah, but if you take architectural material or others, they are also...
It could be a problem that we have to manage.
A dedicated surface process. It's just a question that we have, of course. But I think the project is very nice. It's just an additional question.
In that project, we use material that are not coated. And
exactly. I think in the movie, as far as I could see, this was not coated material, right?
We don't use titanium and zirconium.
Exactly.
The surface was a mill finish surface. It was not an additive surface, just not to add.
Exactly.
Another,
So then I understood correctly the movie.
So the way we moved was in that direction.
Okay. I don't know whether am I allowed to.
In the case in the hot forming component, we have verified too that how is the surface treatment after the forming the part, that we're using a titanium only coating. Titanium passivation to verify that we are able to remove all the lubricant that we use in the process and how they affect the assembly of the component.
Yeah, this will be problem when this alloy will be used, for example, for recycling in aerospace, what is near future. Then aerospace industry already said titanium should be avoided. Yeah, you should not have use titanium in pre-treatment for aerospace industry, and that can be a problem for aluminum recycling, because then you cannot use the scrap for aerospace.
But in automotive, at least in automotive, the material that we're using, the coating is mainly titanium. The coating, the passivation coating that we're using, at least in Europe.
Not exactly. Yeah. If you speak about components or about components, yeah. But if you speak about car bodies, it is different. Car body is still phosphating or some oxylant. There's difference between car body and component.
Okay. Well, thank you very much for the discussion. I think it's an interesting topic. Some other question?
Hi, my name is Simon Buckingham from Volvo Cars. I just want to sort of jump off the previous question a little bit. I think you described really nicely, the sorting technique, collection and sorting, and then sort of the work that you did to select alloys and so on. The bit I'd really like to learn more about was the processing of the alloy. So following the sorting, how did you melt and clean up the alloy? How did you do? Did you degas? Did you use a rotary furnace? How did you find oxide levels and these kind of things? So if it's possible to explain a little bit more around that, I'd really appreciate it.
Well, the treatment depended on the different aluminum alloy producers, so it's not the same treatment for producing a casting alloy than for the sheet stamping or the extrusion. And well, they are defined in detail in one, I think it's public deliverable, so you can find it in the website. But I don't know if you're interested in a specific industry, maybe they can give you answer, because I don't know the exact details of this treatment at the industrial level. I know what we did in Eurecat for the alloy development, but so we did a standard degassing with salt and bubbling before high pressure die casting injection.
Yes, we can add something. We are 3 different aluminum producers: casting, aluminum sheet, stamping, and extrusion. So, but we are more or less the same way to treat the scrap. When we melt the scrap, you have melt, let me say, dirty material is post-consumer. You have the paint, some organic material, and we add a lot of oxide in the alloy, because our very scrap are very little bit oxide. So you have to consider that. You have to destroy the organic material before you melt, and after that you have more than usual treatment with flux, just to remove the oxide. Not only, in my case, not only in the melting furnace, but also in alloy furnace. Also, I think the same. After that, we check the density index, is the parameter that give us the main information, and after we have the gassing process in line and the filtration with the ceramic filter. After that, we made a lot of pot-fat tests to evaluate the level of the impurity. We are pressed to I have to supply the car maker. We have a lot of pressure about that. But in this way, we keep control of the process. But in the end, we have the same value of the, let me say, the total inclusion content in the pot-fat test, the same of the primary producer.
Thank you very much.
No. Any further question? Additional question? Because if not, I think we have, well, it's almost time for lunch, but I wanted to introduce the components, so the demonstrators you will find outside, and if possible, that people in charge of each demonstrator comes to the stage so that you can have the face Claudio, Juan José, Eber, So if you have any specific question, they can answer you. And so it's, for this exhibition, we are going to have 5 demonstrators. Okay, there is, these 5 demonstrators that are the frontal frame that was produced by Endurance, and Claudio, well, it's the person in charge and will be able to answer your questions. The battery box that was done at ASAŞ, and Tutku, well, will be the person in charge of dealing with this demonstrator and answering your questions. The body white part, the hood, that it's from CRF, Stellantis, and Andrea will be able to answer happily your question. And then the B pillar that is done by Gestamp. Juan José Matarranz from Gestamp will be here and happy to answer your questions. And the shock tower that was done by Fagor Ederlan. And Eber is the representative. I think you should leave shortly, isn't it? So if you have specific questions, I think go ahead.
I should.
Okay, Juan José also. If not, I will try to do my best to answer your questions if the corresponding person is not available. Okay. And I think that was all for the session. We are more or less on time.
Thank you.